Engineering is the bottleneck of human progress.
We have already pointed this out in episode 7 on 3D printing. Now, however, we are adding a whole new dimension to the 3D printing game. We enter the world of smart materials and 4D printing.
The smartness of smart materials derives from their capabilities to sense external conditions such as heat or moisture, adapt their shape or their other characteristics to those, and thus effectively deploy a means of information processing.
When combined with additive manufacturing, these 4D printed smart materials can adjust after being printed, allowing to autonomously assemble, disassemble, change, or even repair themselves. Let's explore.
Welcome to the UTX podcast, where we present you a utopia created by technology, presented by your Techniax. I'm Ani.
And I'm Val. And today we're going to talk about smart materials and 4D printing. We will introduce the concepts behind the two topics and then look at their exciting applications. Then we will take a look at their current state, as well as the challenges ahead that needs to be solved. We cap it all off with our signature Utopian day in the life of the Techniax. Let's dive into it.
Let's look into what smart or programmable materials really are. So, both these terms, smart materials and programmable matter, are interchangeable terms, and they're both materials which change their properties in the presence of external factors.
There are a lot of external factors which are being used for different kinds of smart materials. Examples include heat, light, pressure, gravity, magnetism, electricity, voltage, moisture, vibration, acidity, which is measured by the pH value, and chemical or the observation, the presence of chemical compounds.
So, smart materials have the ability to process information and exhibit a response to it. And there are three key factors that we have to consider when talking about smart materials.
Especially when we want to use them for manufacturing, they need to be reversible. Any particular change that happens to them based on outside conditions, that happens to their shape, their form, needs to be reversible by restoring the outside parameter to its original state. So if you turn up the heat, the material changes. You need to be able to turn down the heat again, and the material goes back to its original state.
Another factor is predictability. So you want the material to behave in a predictable way that is consistent to what you would expect it does when you modify the outside conditions in a certain way, so that you can change these materials to your liking.
When it comes to medical applications, you also want them to be biocompatible and biodegradable, so you can use them in combination or inside the body.
Now, the material properties that can change include not just shape, but also solidity, density, color, electric charge, or conductivity. Now, for shape, transformations could include folding, twisting, or curling of the material.
If the materials are specifically engineered to show properties which do not occur as such in nature, we call them metamaterials.
So let's look at some examples of smart materials and the properties that they exhibit to get a better understanding, because we'll find that many of these are already in use in many devices around us today. So in general, smart materials work well with sensors and so-called actuators. And actuators are a machine component that regulate one or more machine parameters.
The first example is piezoelectric materials, and they create a voltage as a response to pressure or heat being applied to them. For instance, when they are being bent. The effect also applies the other way around, as voltage causes the material to deform. The most well-known applications for this is in cigarette lighters and quartz watches. However, piezoelectric materials are also applied in precision instruments and positioning objects, as well as loudspeakers and even precision surgery.
Another example is shape memory, and this allows, shape memory allows alloys and polymers that are deformed by cold, that they can return to their previous shape when heated again, which is why we call them shape memory. And they're applied as solid, lightweight alternatives to conventional actuators.
A well-known example and a good one that serves well to explain what smart materials are is photovoltaic materials, which are applied on solar panels. They convert the sunlight into electrical current. Yeah.
And another example are so-called auxetic materials, and they have the property of increasing in volume when stretched. This is compared to normal materials, which flatten when being stretched. So this means that they also shrink when being compressed instead of increasing in length. And they use these such materials in shoes, for instance, where the sole would expand when running. And it's also very useful if you think about materials that could shrink when compressed together. So this is another very interesting application or example of smart materials.
Electroactive polymers, so-called EAPs, change in size or shape when they are stimulated by electricity. This is especially useful for them being applied for sensors or actuators.
So another one, as you can guess, are magnetostrictive materials as well as magnetic shape memory alloys. And these are materials which change in response to a magnetic field. And they can also be applied to actuators to achieve very fast and precise motion. And the application areas here include medical surgery, robotics, manufacturing, and even in valves and dampers.
Now, further experimentation on those materials, which could also be applied to self-assembly and 4D printing, which we specifically talk about later, is they place emphasis on cellulose materials. Cellulose materials, for instance, expand in water. So you could build something, or let's say you could design something that creates a structure once you put it inside the water. Conductive polymers are also another example of that. Sometimes they are sprayed onto carbon fiber because carbon fiber is quite robust, and then polymers are good for changing shape, for increasing flexibility, as well as different biocompatible and biodegradable materials, such as hydrogel polymer chains, which are often researched on.
And the list goes on and on. And further materials respond to external conditions, such as in the presence of or changes to temperature, acidity values, voltage, light, water, and even other fluids or chemical or biological compounds. So the more we research into smart materials, the more interesting applications and use cases we can surely find.
I think you can already see where this is going. And as Ani has said, there is so much to do with those smart materials. But as Ani already mentioned, using them for sensors or actuators to regulate certain parameters in machines is very promising because they translate the presence of external conditions into changes to themselves or to the material that they're connected with.
So, in artificial muscles, for instance, smart materials can help to elicit the actuation response of these muscles. That would be either an expansion or a contraction or rotation by reacting to outside conditions.
In the aerospace industry, smart materials can happen to save weight. And as you can guess, this is amazing to save cost, to save fuel, to be more efficient. Airbus, in collaboration with MIT, for instance, has built an engine component which controls the flow of air to the engine. Based on changes in temperature or wind speed, the smart material then changes and opens or closes so that more or less wind goes into the engine for cooling. This has the advantage of replacing heavyweight mechanical control systems in aircraft. And there are more applications to this, so a lot of potential to reduce weight in aircraft.
Now, for this next application, we take a big leap from the aerospace industry to the beach. So, researchers from MIT, in collaboration with the company Invena, have actually tested smart materials that can be used to restore coastal areas, specifically at the Maldives. So, their approach is to utilize the wave energy to promote the growth of underwater sand formations by installing adaptive underwater objects as sort of adaptable artificial reefs. And these cause sand to accumulate, and aided by the waves transporting sand, they can use this to manipulate the sand into strategic locations, and thus promote the growth of reefs and restore coastal areas. So uh, we're barely 4 examples in, and you can already see how exciting smart materials are.
And it gets even more exciting. One of the most futurist and somewhat utopian applications of smart materials is in claytronics, or so-called catoms. And those are robotic materials which can interact not just with the environment, but also with each other. And they can form bigger composite structures. They are nanometer scale computers, and they would interact with each other and form tangible 3D objects. This could be manipulated to record and playback shapes, for instance, to simulate a sense of touch, just like we do with audio and video today. Based on these, you could do so-called 4D calls, which would give you an additional dimension of experience from interacting with someone over the internet.
But like this would also give way to applications all over the place. Uh, you could place this in the space of VR or AR and have very interactive environments. You could have this in forensics for crime scene reconstructions.
Or
So
for
the
holograms, yeah.
exactly. So I mean, this goes from everyday tech to very high tech technology. So
Yeah.
this is really exciting,
Ladies and
and
gentlemen, claytronics.
that does seem that does have a very nice ring to it. And this next example brings back an old friend, uh, a big animal in the space of creating future technology, DARPA. And they developed a so-called smart dust, or MEMS, which stands for micro electromechanical systems. And these are basically nanoparticles equipped with a power supply, sensors, and a means of communication. And they made the Gartner hype cycle way back in 2003, and later returned in 2013. And some applications include monitoring plant needs across crops, checking conditions inside concrete structures, or even something called neural dust, which could be implanted in the body to stimulate nerves and muscles, or even monitor the activity of organs. So, again, this is a very crazy technology, which is, thanks to the DARPA, really old, and hopefully it will someday become real. But um, you could prevent catastrophes, you could predict earthquakes. There's so many things you could do with this smart dust. It's amazing.
I'm sure you feel right now that this is somewhat over the top, and that's exactly why we have something that is even more over the top, which is combining the previous two. So if you combine smart dust and claytronics, you arrive at utility fog. And utility fog consists of nanoscale devices that have both the claytronic property of being able to form bigger composite shapes within each other or in combination with each other, but also they are able to sense and transmit data. They have the electronic part in them, like smart dust. And they were conceptualized as early as 1989 as a funny gimmick to replace seatbelts. So think about it, they could essentially sharpen or harden when you put pressure on them, which would have them act as a seatbelt, and they could also communicate if the seatbelt was closed or not. Yet we are not as advanced when it comes to making them reality yet. But yeah, utility fog, smart dust, and claytronics, definitely something to watch out for in the, yeah, let's say farther future. Yeah.
It does sound crazy. Imagine you have this utility fog along the borders of cities, or and you could detect viruses or all kinds of things in the air, in the grounds, down from the nano to the macro. That is very exciting.
Yeah, we come a little bit back into reality, but it's for sure not less exciting because now we talk about something that does have its application, is already being used, which is 4D printing and self-assembly. It is in a quite nascent stage, but if we use additive manufacturing, so if we use 3D printing, and we also put in smart materials, then we arrive at 4D printing. So you can successively print out these smart materials. And these transform after being printed by reacting with the environment, changing their form, changing their shape.
Now, 4D printing usually works based on stereolithography, which means transforming a tank filled with a photosensitive polymer resin through the application of a UV laser. And compared to other 3D printing techniques, stereolithography has the unique advantage of not relying on heat to form or create the material. Now, if you want to, if you don't remember all of the 3D printing techniques, don't worry, we don't either. But if you want to get a more in-depth look or refresher on 3D printing techniques, what is stereolithography or anisotropy, check out our 7th episode on 3D printing.
To come back to 4D printing, oftentimes it relies on anisotropy, which is the opposite of isotropy. And this means that the materials change their properties depending on the direction of the molecules that they are composed of. To make this a little bit more practical, you could engineer materials in a way that they exhibit so-called embedded directionality, which means that the outside or the molecules pointing to the outside are pulling to the outside and thus unfold, or you could also do the opposite, fold the material together, which obviously is quite interesting for those materials to apply to themselves when after being printed out. So an example of such anisotropic properties would be wood, because wood is harder across its grain than along its grain. So it's much harder to cut it across the grain. However, for this to become a viable application, it might require complex fiber or even molecular simulation and computation to approximate, to simulate the aggregated material properties that are going to happen. So think of this as like a computer model similar to a swarm of molecules that are interacting with each other and trying to figure out what is going to happen. Also very exciting to bring in computer science in there. Think as a simple example, as already mentioned, the outside molecules of a folding material. So they fold together while the inside molecules remain static. In order to fold the borders of the materials to the inside, would have the inside remain static.
So by being able to manage these materials and how they fold themselves, you could form new structures and um, create large structures that could dynamically self-assemble themselves, self-repair, and even self-disassemble and fall back into a flat packaging-ready state. So next time you order a piece of furniture at IKEA, you won't have to sit hours and assemble it yourself. It will just assemble itself. And if you're moving back out or would like to sell it, you can just give the order and it will fall back into its original state, ready for reuse.
When you know that DARPA is involved in developing a technology by funding, by collaboration in the space, by applying researchers, and when you additionally know that MIT is also hot on the topic, then you do know that smart materials and 4D printing is very promising for the future. And in the case of MIT, since the early 2010s, they have built this self-assembly lab, which is exclusively focused on those smart materials. And their prime researcher, or at least appearing in the public, Skylar Tibbets, has been advocating this since early in 2012, has been done multiple TED Talks on it, actually. And the self-assembly lab came up with prototypes showing the concepts of these smart or programmable materials and 4D printing since then. One of their first objects was a printed composite polymer chain, which folded to display the word MIT when submerged into water.
Yeah, I remember seeing that video and thinking back then how exciting it would be if we could control materials at a molecular level. And speaking of exciting, smart materials and 4D printing unleash massive benefits, and not just for producers or production organizations, but along the entire supply chain of products. So from product innovations to manufacturing to shipping to logistics, it really leaves no stone unturned.
Let's talk about the former, so product design and innovation. 4D printing removes the barriers from designing new and versatile products by marrying the useful properties of 3D printing, which is great for rapid prototyping and customization of prints, with the circumstantial embedded reactions and self-assembly capabilities of smart materials. As an example, the company Autodesk has developed a cloud-based software called Cyborg, which allows users to simulate and study the self-assembly behavior of 4D printed smart materials based on CAD models, so computer-aided design. Remember, this is the underlying visualization file type that is being used in 3D printing most of the times. So researchers from Harvard Medical School, once again, also appearing a lot in our episodes because they're very active and well-funded, have even developed the software Cat Nano, which has DNA in its name, which lets you create 3D models of nanostructures that self-assemble based on DNA nanotechnology.
Now we move on to the production stage, where this process of producing complex products that consists of dozens or hundreds, or in some cases even thousands of components that traditionally need to be assembled with human labor, could be greatly simplified and entirely automated. So think for instance shoes, a complex product that's made out of dozens of different parts that are stitched, stretched, glued, and stitched together. But now they would just come pre-shipped as a flat piece, and then they would self-assemble around your foot for the ideal fit. So a lot of improvements can be made in production.
When it comes to shipping, you could think of 3D printing and 4D printing as sort of IKEA for the whole economy. So instead of delivering the whole furniture, you can deliver any material just flat or in an ideal shape for it to be transported. Remember that Ani said that oxidic materials, they can be compressed. They can be actually compressed to a smaller shape. So this is very useful in order to have them shipped in a flat way, for instance, and then having them self-assembly after you unpack them and going to their final form. But then also in the case of 3D and also 4D printers, maybe you don't even need to ship anything apart from the input materials, the filaments, etc. You essentially can print all of that at home. This, however, might be a challenge to logistics because you need to ship those materials, and especially the smart materials, in conditions which cause them to remain stable during transportation, because you don't want to, for instance, transport a flat smart table and have it unfold already during transportation and it cause some disruptions, for instance, especially when it is in an airplane or something. You definitely want to avoid that.
So let's move on to other applications, and this time entirely dedicated to medical, because 4D printing can again do a lot for medicine. So one area is the manufacturing of personalized medical tissues and implants. So this would be in case of organ transplants, bone reconstruction, skin grafts, or even stents and nerves. So there's a lot of potential. Think of it as programmable stem cells that we could use in combination with mRNA technology to have the body heal itself, much like smart materials do, in a much quicker and effective way.
Yet they can also be introduced as drug delivery systems. So when we say that these smart materials react to outside conditions, those outside conditions can also be within the human body. And in this case, hydrogel could be used as a drug carrier, which achieves a continuous release of the drug into the body because it reacts based on human body temperature and moisture, which causes it to release the drug, yeah, continuously.
Yeah, there was even back when Google Glass was still a big project, there was still the idea of measuring, um, for especially people with diabetes, to measure their blood sugar through the iris. And so if you would combine that with, say, a new type of insulin shot for people with diabetes, they would no longer have to take shots every so often, but they could just refill that supply once a month, and it will be much less of an inconvenience. So there are a lot of applications when talking as drug delivery systems, but there's also a very adjacent topic that is reducing the invasiveness of surgery. So surgical implants can now be printed out in smaller shapes and can be actuated later to reach the full shape inside the body based on its reaction to temperature or moisture. So this would allow the implants to reach locations that would have not been reachable with former completely formed implants. And the same has been tested out to block the blood flow for cancerous cells in order to starve them. And the material in use was a shape memory polyurethane that was a specific type of polymer. So again, there's many applications of being able to control or manage the volume of implants.
Including teeth implants. And the French orthodontics company Anenke uses 4D printing, uses digital scans and biocompatible polymer resins to create custom fit teeth devices. In the future, these could be made with programmable material to have them push other teeth in the desired place once you put them inside the mouth.
So instead of wearing braces, you could just push your teeth around effectively, or
Yeah.
or is it like sharks? If a tooth falls out, another one grows back.
Yeah, you can really print custom made shapes and have them extend themselves and slowly push the teeth to the desired direction afterwards.
So you could create very exciting Halloween costumes.
That as well. Yeah.
But we now move on to not just medical, but again to other industries and interesting use cases. Uh, One would be water pipes, and water pipes are traditionally very expensive infrastructure investments into pumps and valves, which have to then be buried into the ground. And once they're assembled there, there's not much capacity to fix or really react to any changes in demand. So to increase flow rate, for instance, you need to effectively replace the water pipes. But if you would, for instance, have pipes made out of smart materials, which could expand and contract to adjust to the flow rate and capacity, you could massively save on cost, labor, and time, and potentially even save lives.
Now, there are some concepts which turn up over and over again in our podcast. It could be, for instance, genetics or also protein folding, because it's just very important. And after recent breakthroughs in relation to understanding how proteins fold based on amino acids, how they fold into their final three-dimensional structure, 4D printing could visualize that process and allow us to study that further. This would include printing a flat string of fake amino acids, which are then capable of folding into the desired protein structure after being printed.
So very exciting indeed. And now we get to not the last one, but again, it's a very long list, and we have to try to contain it within an episode. So we just cherry pick the top most exciting and influential or impactful use cases. Another one would be extreme conditions. So in areas like space or deep underwater. So with the absence of sophisticated machines, manufacturing options, self-assembling matter could really be something very useful. Think, for instance, instead of having to send complex devices or biospheres or structures to Mars or to the moon, you could just send a few tons of materials, one rocket at a time, and it just assembles itself there. No need for large operations, human labor, and increased danger. So it's really exciting beyond just being an exciting technology. It's also very interesting, as we saw, if we combine it with other futurist or utopian technologies.
Now, every time that we try to put a number on the market of those emerging technologies that we look at, that is quite difficult once you face a technology like smart materials and 4D printing that can be applied to so many different industries, but also is an umbrella term for so many different technologies. And if we look at the smart materials in general, and however we define it, it does already have a significant size. The market size was estimated to be $33 billion by 2016, and the market is expected to grow annually by around 13% until 2025, which would give it a market size of $100 billion, give or take. As so often, I compare this to the fintech industry, which roughly is at around $100 billion. So just that you have sort of a reference size. So that would be roughly the size of the fintech market today, right? And DARPA continues to fund research activities in the area. And as you have seen, MIT and Harvard are also in the space. And with such backing, it is easy to imagine that those projections might become true or might even become, conservative.
Now, in contrast to smart materials, 4D printing as a market is still quite recent. And as a concept, it has been around for less than 10 years. So by 2019, estimates regarding market size were at $65 million. That's right, million, not billion, as was the case for smart materials. However, there is an expected annual growth rate of 33%. This means that by 2025, the market could be expected to grow to $300 million, essentially adding 1/3 of itself every year. And the result is surprisingly so very small if you compare it with smart materials or other utopian technologies that we have looked on. But it, of course, also relies on further development, especially development into smart materials. So this is a very young market. It's hard to put a clear figure on it, and it's even harder to put a growth rate or expected growth rate. But if companies or institutions like DARPA and MIT continue to invest and bring it to prominence, these numbers will someday appear very small.
Exactly. But as for now, and now as we're coming to the challenges, 4D printing, as you've said, is less than 10 years old. So really in an infant stage. And as you've already also said, we need to research on smart materials and especially how smart materials use in reaction with 4D printing. We see this also similarly when we look at 3D printed food, where you also need a food that exhibits certain properties in order for it to be useful for 3D printing. Same is the case for smart materials and 4D printing, especially if you look at all the medical applications that we've talked about, when they also need to be biocompatible and biodegradable.
And another challenge is finding cost-efficient materials. So materials that are lightweight, robust, strong, and flexible, and that are also suitable for 4D printing, and exhibit useful properties by making them programmable to outside circumstances. And in this case, that'll be a 4D printer usually formed by UV light. So this is another tricky aspects that needs just a lot of research put into it.
And one of the major roadblocks to both smart materials and 4D printing is scalability. For those smart materials to be synthesized or for them to be introduced or produced in industrial grade, a lot of research has still to be developed. And for any 3D printing use case, while it is great for prototyping, while it is great for customization, personalization, it is usually not great for mass scaling and mass production. And also 3D printed materials have sometimes shown to degrade significantly over time, which poses challenges towards improving durability and the lifespan of 3D and also 4D printed structures.
And another challenge, and Val already mentioned this before, are that in logistics, we need to protect these smart materials against light, heat, pressure, and other external factors that could trigger certain changes. So it would be uh, quite disastrous if smart materials were to start assembling themselves during transportation. Maybe there's a way to maintain homeostasis. Maybe there's a way to create or create these smart materials that react to different conditions, and thus you can manipulate one of them to prevent a change in the other or a reaction to the change in the other. But as of now, logistics of smart materials is still a tricky issue.
And remember that there is sort of two different kinds of smart materials. That are those that you sort of have organically by assembling molecule structures in a way that these smart materials then exhibit certain properties. And there is the other way where you introduce robotics or electronics to the process to sort of make them smart, make those materials smart from the outside. And in 4D printing and self-assembly, in many cases, the latter is being used. And introducing additional electronics means additional weight. And this is not just introducing additional weight, but also added cost and production complexity.
And lastly, we look at a more economic and societal issue is that 4D printing or self-assembling materials would cause for global reductions of human labor in manufacturing processes. And this would cause layoffs and mass unemployment, especially in developing countries. So the issue here would be more a logistics problem. How do we make sure that those people, or how can we effectively use them? In the long run, of course, it's more efficient for humans to not waste time in mundane tasks such as manufacturing. But in the short term, these layoffs and mass unemployment are definitely an issue, or will definitely be an issue.
So we've done all the chores now. We've crawled through the mud of challenges, be it economic, societal, or be it related to the technology. And now we come to the fun part, which is the Utopian day in the Techniax life, and today powered by smart materials and 4D printing. So usually we start these Utopian days during the week, but now it's a Saturday. And today is the big day because I'm moving to a new place. I'm super excited about the relocation because it will be far from a tedious process. You've heard right, it will not be a tedious process. Why? Because the majority of my possessings are made out of programmable and oxidic materials. And what's more, they have connectivity and I can control them with my smartphone app. I pull
or
it
your
out,
BCI.
or yeah, it could be even my BCI. I pull out my smartphone or activate my BCI, and then I tap a couple buttons or think a couple thoughts, and my items are flattened out and reasonably compressed together, ready to be shipped to my place. Nothing easier than that.
And I woke up quite early. I did not expect it to take 5 minutes. I thought it would take maybe an hour, but it turns out that I was done in 5 minutes. So I decided to turn on the news, and I got to saw the latest breakthrough in the process of colonizing Mars, which is astronauts are now building the first human-made town outside of Earth. So they're using 3D printers and self-assembling materials, which autonomously form into desired shapes and structures and forms after being stimulated. So not only am I just moving my things to a new place, humanity is moving entire cities and townships to other planets. And instead of taking it like it used to take several hundred years ago, months or years to build a city, it now took them what they stated in the news, merely a few hours.
Wow, amazing. Now, coming back to my own little world, let's say, during my relocation, I also decided to do some nice little interior design because, as if you follow this podcast, you already know that I'm a big fan of architecture. I care very much about this. And so my new piece of furniture arrives in a box. I open that box and I just tap the table in a certain way, and then it constructs itself. The smart textile materials are bonded to a wooden frame of the table, and the shape is formed once I purposefully touch with some pressure. Really nice.
It really sounds like a scene out of a Harry Potter movie. So I also remembered, and good luck, they arrived today, are my customized hiking shoes. They finally arrived in the mailbox, and now the 4D printing process can start. And so this one is a special shoe. By using a combination of carbon fibers and shape memory polymers, my printer is able to print out a flat structure which keeps building into a robust but customizable shoe size as I put my foot into it. And these hiking shoes even come with an inbuilt AI and an on site edge computer. And they use the data input from me hiking, from the feedback that my foot and my body are giving, to create the ideal shoes which adapts to different terrains, different altitudes, to always be the perfect shoe that my feet need, to be the only thing. And I don't even have to remove them. I don't have to wear socks beneath them because at night they just turn into very thin, breathable socks. And it's amazing. And I really can't wait to start ordering all kinds of things, smart clothes that change appearance. I really look forward to it.
What an amazing weekend it is. Even though I'm relocating, even though I'm moving my stuff, I have a lot of time to do all those things. And I would really love to go to a hike right now, but I watched the weather and apparently it's going to rain. So I used the time to read some article about how cancer therapy has been massively accelerated and side effects of those therapies are really a thing of the past. The way that medicals do this, the way they achieve this, is by printing out the personalized printing out the personalized nanoscale robot that is made from DNA strands. This is then injected into the patient's body, and there it unleashes the antibodies, but not randomly, but specifically once it reaches the right location and recognizes cancerous cells. It can do that by sensing and detecting the body's temperature and moisture levels and being able to recognize these cancerous cells. Really fascinating.
And I even remember in one of in the interview, one of the researchers mentioned how the next step, and this would probably come out in the coming months after this, would be how these new nanoscale robots can now coerce cells to produce more telomeres, essentially to de-age. Or rejuvenate certain parts of the body or even the entire body without having any side effects. So the implications of these nanoscale robots are just uh, immense and incomprehensible. So I'm done with moving, even though, if I'm being honest, I did not move a single finger, only while uh, only while for disassembly and assembly I had to press twice. So I guess that is pretty tedious. So I didn't have much to do. I settled in, everything was assembled by itself. I called a friend of mine, and we decided to fiddle around with a hologram 4D version of a simulated house that we continue building. It's kind of been our little pet project during weekends, and we spend some time on that, and then we play a martial arts video game where Claytronics supplied this extra realistic feeling of getting hit every time the opponent successfully lands an attack. And of course, we can customize or use the smart material in our tables to create this 3D environment, interact with each other and the environment. We even played some paintball. It was a lot of fun. It was as if we were in the wild, actually hunting, having fun. What a fun 4D call session! It's really changed the way I have or I entertain myself. And with that, I decide to go to bed in my new bed, which is, of course, also powered by smart materials. Um, it's even it's powered with an AI and an edge computer of itself to ideally calculate the temperature, to avoid any blue lights, and to subtly fake a sunlight in the morning, so that I can have a fully rested night and wake up prepared to charge it the next utopian day.
Amazing. Wow. All powered by 4D printing and smart materials. If you've enjoyed this episode, make sure to subscribe to YouTube, to follow us on Spotify, or to follow us on Medium. And as we've already suggested in previous episodes, there are now also clips about these episodes on YouTube, so short versions, short parts, which we consider interesting about this whole discussions. And yeah, I think that those are the most important announcements.
Yeah, we have also we're also on Instagram and Twitter and other social media platforms, so feel free to follow us there. And uh, as well, I'm not sure what next week's topic is again, but
I think it will be future of energy.
oh, interesting. Oh, yeah, energy is a larger topic. I think this goes beyond the utopian day. I think this is the utopian life of humanity then. But I guess you have to wait another week to find out more on the future of energy. And as always, stay utopian.
Stay patient as well. Your Techniax.